All right. Good morning. Happy to see all these nice, friendly faces 8 o'clock in the morning. Anyway, today I'm here to give you an update on what we've been doing at SRI relative to Brillouin energy experiments since ICCF-20. Are we up? We're up. This is just a quick outline. Talk about some of the earlier pressurized gas results and the new designs and calorimetry, and then give you hopefully a taste of the results of what we're seeing so far, and hopefully a little bit idea what we're trying to go forward with. So first, a summary of what's happened before up to about ICCF-20, and that was there's about 100 experiments performed in 10 cores, and I'll explain to you what I mean by a core. But we've been working in the nickel hydrogen system at elevated temperatures for over 2 years. So there's enough excess power, and it was reproducible enough to convince us to keep moving forward. There are pulses sent through these pieces of metal, and I'll show you a photo, a diagram in a minute. And experimental results are consistent with Robert Goddard's controlled electron capture hypothesis, which I won't go into today just for brevity. And by changing the pulse parameters, you can alter the excess power by between 25 and 100%, and you can actually turn it on and off by putting in the same amount of power by just changing the parameters of the stimulation pulses. You can turn it on and off. So this is more or less what one of them looks like. I'll stick over here. Well, yeah. So starting on the inside will either be a metallic or a ceramic tube, and sometimes there's a heater in the middle, but there's always a temperature sensor in the middle. On top of that, on the purple is a stripe of plasma sprayed copper. That's just a return line for the pulses. And then after that, which is actually dark blue, but might look black to you, is a ceramic, usually alumina, and that's also plasma sprayed. And then on top of that is the nickel, that's plasma sprayed as well. And the numbers up there are approximate. And everything is porous, and the pulse is sent between the nickel and the copper, so it's going through the dielectric. And these are fast rise time pulses, and they're fast enough, a few nanoseconds, that it induces the skin effect, so most of the current is within the first few microns of the nickel at the alumina interface. So there's an idea what the pulse looks like. We have just a long dead time. Generally, the numbers are less than 1% duty cycle, but they can be more when we go to low voltages so that we keep everything constant. And the pulse width can change as the amplitude and the dead time repetition rate. This is how we measure it. There's a very nice oscilloscope taking 5 million points a second, no, 5 billion points a second, anyway, to give us the voltage at one end, and then we get the voltage at the other end. So in this chart, you see the voltages and the current plotted on the left axis, and the power, instantaneous power, plotted on the right axis. So you measure V1, you measure V2, that's what they look like in red and blue. V2 also gives you the current because there's a current shunt right up next to that end of the core. And so that's the current down here in black, and then multiply the difference of the voltages times the current, and you get this power over here, this instantaneous power. This is what the interface looks like. We measure 57 parameters in the sequence that we use. We use sequences to automatically stimulate it. Some of them run for 100 hours, and we just take the data and analyze it when it's ready. There's some loss in the termination resistor, that's designated here, and in the switching transistor. As you can imagine, at these currents, you're getting a lot of heat there. So those actually have water flow heat sinks, so we're doing some mass flow calorimetry on those two thermal losses. I was going to show there are temperature sensors all over. There's one in the middle. There's a couple, or sometimes two in the middle, two in this heat spreader, another two out here in the aluminum. Between the heat spreader and an aluminum shell is a ceramic insulation. Outside the aluminum shell is an acrylic shell, and there's water flowing there to keep it at 25 degrees C. This is just another way of looking at it. The thing I'll point out is there's a feed through up here to send in and return the pulses. Everything else is pretty much the same. There's argon actually flowing through that ceramic insulator between the heat spreader and the aluminum, and there's argon outside the reactor just for safety purposes, since we're almost always using pure hydrogen or pure deuterium. So, yeah, it's the static gas. We keep it at a controlled pressure, top it up as necessary, which is very rare. It's not flowing. Operate from 200 to 600 C. You saw the outer block is constant, so that's our isoparabolic calorimeter. The pulse power from the stimulating pulse is held constant by changing the amplitude, the repetition rate, or the pulse width. Actual pulse power is measured, as I showed a couple of slides ago, directly. And then we do two types of calorimetry. Power compensation calorimetry, where the heater power is set to a constant temperature, and as you add pulses to it, it lowers the power going into the heater, and that difference is part of our calorimetry. And the other one is constant heater power calorimetry, as you normally do in isoparabolic calorimeters. You keep the heater power constant and just calibrate it at different heater power steps so you can calculate how much power is being put in by the pulse as it adds on to the heater power. Operation. Again, like I said, mostly in H2 gas, sometimes D2. We found we don't need to operate in argon or helium anymore. It's just all the thermal parameters are so different, it just gets too confusing. So we just leave everything in hydrogen most of the time. Again, 200 to 600 C, adjust everything. So first you do that pulse stream with low voltage pulses. The concept in the hypothesis is that below a certain threshold, you're not going to induce this controlled electron capture. And so you do that, you get your constant pulse power, get all your parameters calculated, calibrate your system, and then you go and do the exact same thing at the exact same pressure and temperature with much higher voltage pulses. Talking somewhere about 30 volts versus 350 volts. And you measure and record everything, more than everything you need, every 10 seconds, and including the hydrogen and oxygen concentration outside the reactor for safety reasons. And then you compare that output power or heater power compensation, depending on the method of calorimetry, of high voltage pulses versus low voltage pulses. Everything else held constant. The assumption is you should have the exact same thermal response. And occasionally we'll go in there and do a DC calibration just by passing a DC current across the nickel without touching the copper or the alumina. So we have two methods of calorimetry we've been employing: the steady state, which is like the old-fashioned, good, the relatively well-established method, where you just put in increase the heater power and wait, and depending on your time constant, you can wait several hours and call that your steady state temperature versus heater power. And then you do that with the pulses, and again, the high voltage versus low voltage, and that's how you calculate the reaction. Delta H of reaction is just the heater power compensation, how much it's been reduced for a low voltage pulse compared to how much for a high voltage pulse. And then you could they like to use COP, not everybody likes to use it, but then you just get your delta H that you calculated divided by the amount of power that you know went in from your low voltage pulse stimulation. Another method we use is what I call dynamic stimulation, and in this you're sending in essentially waves, half sine waves of combination of both the heater and the stimulation power. They're changing all the time. There's nowhere near steady state. And you do that for 40 hours or up to 100 hours, depending on the design. And this gets you an idea of what the model is. And there are simply, as it turns out, there are only 4 terms that are important. That is the K, which is the delta T between the core and the heat spreader, and the other K, which is between the core and the outer temperature. And then there are 2 heat capacity terms, and in front of those are actually all 3 parameter binomials. And then you fit that in a MATLAB program under low voltage power, and in reality, maybe 9 of those 12 or 8 of those 12 fall out as 0, and you end up with 4 parameters that you know define the system. And then you do that with the low voltage stimulation, and then you apply those same coefficients that you got from the MATLAB in the low voltage stimulation to your high voltage stimulation, and then just divide that into by the low voltage stimulation. This is just an idea of what the raw data looks like. On the left axis is heater power or temperature, and the heater power is in blue, the temperature is in green, and then on the right axis is the power that's measured by the oscilloscope going into the core, and you see that's up to like 6 watts that goes in. And this is what some of the steady state results look like. So instead of just doing it at 2 different voltages, we've done it in several voltages. So the y-axis, we've plotted voltage of the pulse, and the x-axis, we've taken that heater power compensation and divided it by the power measured by the oscilloscope. And so at, say, the green line at 250 degrees, down here at about 35 volts, you get a ratio of like 0.58. But then you keep increasing the voltage, but maintaining the exact same power going into the system. And you see as you get up to about 350 volts, you're way over here at like 0.73, 74. So it's not a great number, but it's a reproducible number, probably 25%, something like that. And then you see a very similar thing at 275, no, at 300. And then when you get past 300, interestingly, that ratio of the heater power compensation is pretty much the same at 350 volts as it is at 35 volts. So it tells you that you're not creating excess power, and it also gives you a built-in calibration that you know what's going on. And this is some of the summary from the steady state stimulation results. And it's very similar to what you just saw. If you stay below 350, you get numbers, COP numbers that are over 1, above experimental error, and then 350 and up, the numbers are pretty much equal to experimental error, so you don't see those at excess power. Oh, I got a few minutes, good. So this is what that pulse stimulation looks like when we do the dynamic stimulation. And this is a combination of the heater and core power in blue that was determined from the low voltage pulses, and then the delta T's measured in the high voltage pulses had those same coefficients determined from the low voltage applied to them, and that's the light green. As you can see, there's no steady state, except I finally asked them, why don't you do something that stands still for a while so we can watch it instead of having to do all of this computational stuff. And so they held this constant for about 3 hours, and as you can see, the calculated power, output power with the high voltage pulse is about 5 watts above what we got with the low voltage pulse at the same input power. And those are similar numbers over here. And you can see those COPs are, again, not overly exciting, but between 1.2 and 1.3. And over here, yeah, same sort of number. So we've done that a bunch of times. And this is what some of the dynamic stimulation results look like. And again, at different temperatures, but none of these are above 350. So all of them are showing some reasonable powers at delta H, as I said, the difference between the low voltage pulse and the high voltage pulse, up to 5 watts. And then calculating the COP using that method. Again, those numbers in the 1.2 to 1.3 range. But interestingly enough, when we did all of that, we changed the way we did all of our calculations compared to what we reported earlier. And so I went back and used the earlier method, essentially put in a fudge factor so we could compare it to where we were earlier, so that at least we could see whether or not we were making progress. And when you do that, and progress was, we were getting numbers about the same, about 1.2 when we used the old method. And when we went back and reapplied that method to the new data, we got numbers closer to 1.5, I mean at 1.6, which was important to convince us that we were making progress so we could go forward. So let me sum up what we've learned. So these are reactions stimulated by electrical pulses, very narrow, very fast rise time electrical pulses on coated nickel powders. And these are very porous nickel powders. Experiments in hydrogen deuterium 200 to 600 C, and heater-only power and heater and pulse power, and then power compensation mode. 500 experiments on 100 different nickel-coated cores and 6 different reactors. So in the last 2 years, we've upped our game by an order of magnitude with respect to the amount of runs being made. And again, COPs between 1 and 2, electricity in, heat out. And of course, as everybody else is still doing, we're still optimizing our metallic composition and metallurgy, and also, since most of the group is electrical engineers, they're always tweaking the pulse parameters, finding narrower pulses, sharper rise time pulses, and we regularly update and improve the calorimetry. And I need to acknowledge Berlin for their generous support at SRI. This is an old picture of the group in their conference room. They actually have a lab. About half of the experiments are being run at SRI, half are being run in their third floor walk-up, as I refer to it, in Berkeley, which is behind that rear door. And I want to thank you for your attention, but first want to note a personal note on the bottom just for your information. And thank you.
I want to thank Fran because he's helping getting us back on time. We do have time for some questions. Okay.
Have you got any numbers for the impedance or the RC frequencies from the aluminum oxide? Is there a capacitance there? Have you tried to match it?
Oh, yeah. That's, like I say, we've got a room full of electrical engineers, and that's what they do for a living. And the impedance is in the 2 ohm range.
Okay.
And they're always measuring TDR and minimizing capacitance.
Have you tried using multiple layers and going through them?
We have done that, but they weren't very successful, so they gave up on that since that's a lot harder to make. Tom.
Hello, Fran, could you say something about the material, the pressure, post-analysis, helium, anything like that?
Okay, we're not doing any post-analysis. We do have, in 2 of the 6 reactors, we have an online mass spec, but it's just an RGA, so it's not telling us anything too anomalous. I'm sorry, I should have mentioned, most of this is done between 8 and 10 bar of hydrogen. And analysis, we're not doing any gas analysis. My mass spec is still being tweaked. And occasionally, they've tried to get people to do isotopic analysis on the powders, but nobody really seems to be interested or capable of telling if anything's happening to the nickel.
I'm sure Francesco has a quick answer or
Sure.
question because he wants time for his presentation.
First one, good paper. Second one, we have long experience about pulsing, palladium wire, so on, and we found that the surface temperature is really larger than of the bulk because of skin effect. Do you have an idea which one is your surface temperature?
In the nickel,
Yes, okay. Where you give pulse, sure.
well, because nickel is paramagnetic, it has the skin effect, so most of the current is going at the interface.
Okay.
But this is just plasma sprayed, so it's very random. There's no controlled morphology or anything.
Okay, thank you.
Okay, our next speaker is Mitchell Schwartz, and if you can come up here and we'll get